All right, so get this. What if we could simulate the entire universe? And like not just some rough copy, but like down to the last atom, the last quark.
It's a question that just kind of blows your mind.
Yeah.
And the really wild part is that, this isn't just some idea from science fiction. This gets at the core of how we understand physics.
And that's why, for this deep dive, we're going to be talking about Richard Feynman, the bongo-playing, Nobel Prize-winning, all-around legend.
Oh, yeah.
He actually tackled this question in one of his papers, and trust me, it gets strange.
Yeah, Feynman, he was known for asking the big questions. And in this case, he wasn't content with just approximating physics on a computer, the way, we do a lot today. He wanted to know if we could actually create a perfect replica, a simulation indistinguishable from the real thing.
Okay, so hold on. Before we go too far down the rabbit hole here, why does this even matter? Is this just physicists showing off or something?
No, it's way more than just showing off. You see, if we can't perfectly simulate the universe, even with everything we know about physics, then that means there's something huge missing from our understanding, right?
Yeah.
Like, either our laws of physics are wrong, or there's a whole other way to think about computation that we haven't even imagined.
You're blowing my mind already.
Yeah.
So where do you even start with a problem this big? Like, how did Feynman even approach this?
So, like any good scientist, he starts with some ground rules. His first rule was that the simulated universe had to be what we call local, meaning that events are only influenced by their immediate surroundings, like a domino effect.
Okay, so kind of like those, what are they called? Cellular automata, where you have a grid and each cell changes based on its neighbors.
Exactly. Feynman believed that this idea of locality was crucial because it puts a limit on how much information the computer needs to keep track of as the simulation gets bigger. We can't have infinite computers.
Right, no cheating with a computer the size of a galaxy to simulate a galaxy.
Exactly.
All right, so what was his second rule?
His second rule was all about being practical, keeping it real. He said that the size of the computer needed for the simulation should only grow proportionally to the size of the simulated universe,
Right.
not exponentially. Basically, no cheating with infinitely large computers.
Keep it real. I like it. That's a good rule. It sounded like he was setting some pretty strict boundaries for simulating a whole universe.
He was. And this is where it starts getting even more complicated, because one of the first major challenges that he ran into was time.
Yeah, time, that's a big one. How do you represent something as constant and as flowing as time on a computer which itself operates in time?
That is the million-dollar question. I mean,
Okay.
think about it. Normally, computer programs imitate time in a very step-by-step way.
Right.
One instruction after another.
Right.
But Feynman wanted to represent all of space-time at once.
Wait, all of space-time at once.
Yes.
Are we talking about some kind of cosmic freeze frame here?
Not exactly a freeze frame. Think of it more like a space-time view, where the past, present, and future, they all kind of exist together within the simulation.
Okay, so it's like instead of watching a movie frame by frame, you're experiencing the whole movie all at the same time.
That's a great way to put it. And this idea of time as a dimension, it's not just some abstract thing.
Yeah.
Some theories in physics actually already play with the idea of time going backward. Like, think about positrons. Those are the antimatter versions of electrons. And one way to think about them is as electrons going back in time.
Whoa, time travel at a particle level. Things are already getting weird and we're just getting started. But wouldn't the math behind representing all of time at once be incredibly complicated, like even for a supercomputer?
You're exactly right. I mean, just representing all the points in time simultaneously is hard enough, but actually performing calculations, that might be a whole different story. And as you're about to find out, things get even more complicated when we introduce quantum mechanics into the picture.
So we've got all of space-time happening at once, particles maybe traveling backward in time, and it gets even weirder than this.
Oh yeah, we're just getting warmed up, because now we have to add quantum mechanics into the mix.
Quantum mechanics, didn't Feynman say that nobody really understands quantum mechanics? That's where things get really fuzzy, right?
It doesn't. It really throws a wrench into this whole simulation idea.
Yeah.
Here's the thing. In quantum mechanics, you can't predict outcomes with absolute certainty. The best we can do is calculate probabilities of different things happening.
So it's like flipping a coin. We know it's going to be heads or tails, but we don't know which one until it lands. How do you simulate that on a computer? They're all about definite answers.
Yeah, that's a tough one. See, to simulate a quantum system, let's say even just a single particle, we need to think a little differently.
Okay, so let's say we've got our little quantum particle. What do we do?
Well, in quantum mechanics, we would usually describe its state with something called a wave function.
Wave function. Okay. I'm imagining like a wave in the ocean. Is that right?
It's a little more abstract than that. Think of it like a map that tells you the probability of finding this particle at different locations. So instead of a single point, it's more like a blurry cloud, showing all the places it could be.
Okay, I think I'm with you so far. This is where I have a feeling it's going to get complicated.
And you would be right, because as soon as we start talking about more than one particle, the amount of information we need to describe them, it just explodes.
Explodes. So you're saying, like, if we have twice the particles, we don't just need twice the information.
No, no, no. We need exponentially more information.
Exponentially.
Yeah, we have to keep track of all the possible arrangements of those particles. And when you're talking about billions and billions of particles, well, the amount of information you need is just mind-bogglingly huge.
So even if we had a computer the size of, like, the entire planet, it wouldn't even be close.
You're getting it. And that's just for a tiny speck of matter. To simulate the whole universe this way seems pretty much impossible.
So did Feynman just give up at this point?
Not quite. Remember Feynman? He was known for thinking outside the box.
Yeah.
So he asked this really radical question. He said, what if, instead of fighting this randomness, what if we embrace it?
Embrace the randomness. I mean, how do you even do that with a computer?
He thought maybe the key was a completely different kind of computer, something called a probabilistic computer.
A probabilistic computer. So instead of giving you one answer, it would give you like a range of possibilities.
Exactly. Imagine running a simulation, and instead of getting one outcome, you get a whole bunch of them, each with its own probability. Kind of like repeating an experiment many times in real life.
So it's like a snapshot of all the different ways things could go in the quantum world. Pretty wild. Did it work? Did he figure it out?
He actually made some really amazing progress. You see, he found a way to represent these quantum states that, at first glance, seemed like something a normal computer could handle. But, and this is a big but, some of these probabilities, they ended up being negative.
Negative probabilities. That's like saying there's a negative chance of, I don't know, winning the lottery. How can a probability be less than zero?
That's the thing. It just doesn't make sense in our normal way of thinking. And this wasn't just some mathematical quirk. It pointed to a much, much deeper problem, something fundamentally different about how information works in the quantum world.
Negative probabilities, huh? Can't you just, I don't know, invent some new kind of math where that makes sense?
I wish it were that easy. But Feynman wasn't content with just explaining it away with math. He wanted to show why it was a problem in the real world. So he came up with this really elegant experiment to illustrate the point.
Elegant, that's a good word for Feynman. So what was it? What was the experiment?
It all had to do with something called photon polarization. You think of it as like how light waves vibrate. So imagine shining a beam of light through a special kind of crystal, calcite crystal.
Okay.
This crystal splits the light into two separate beams, one where the photons are polarized vertically and one where they're polarized horizontally.
Okay, so one beam in, two beams out, each one vibrating in a different direction. How does this connect to those negative probabilities?
Here's where it gets interesting. Let's say you take one of those beams, the horizontally polarized one, and you pass it through another calcite crystal. Depending on how that second crystal is oriented, you can predict the probability of a photon passing through.
Right, so we're kind of filtering the light based on its polarization.
Right. But now, let's bring in entanglement. Imagine you've got these two photons that are linked. Even if they're really far apart, it's like they're two sides of the same coin, even if you flip one coin on the other side of the universe.
Okay, two photons linked. This is getting kind of spooky, isn't it?
It is, and it's this spookiness that our classical way of thinking just can't handle. Because here's the thing, if you measure the polarization of one of these entangled photons, you instantly know the polarization of the other one, no matter how far away it is.
You're telling me if I measure a photon here, I could know something about another one that's light years away, instantly.
That's the whole point. And it's a big problem for our simulations, because classical physics, even with all its probabilities, can't fully account for that. Feynman showed that the maximum probability you could get using classical logic to predict the outcome of this entanglement experiment is lower than what quantum mechanics and real experiments actually show.
So there's a real difference between what our classical intuition would say and what actually happens in the quantum world.
Exactly. And it means that there's something fundamentally different about how information works at that level, something our computers, even those probabilistic ones, just can't seem to replicate.
So where does that leave us? If even Feynman couldn't figure out how to simulate the universe perfectly, should we just give up?
Not at all. It just means we need to keep searching for new ways to understand things. What Feynman did was show us how deeply connected physics, information, and computation really are. And even if we can't perfectly simulate the universe, trying to do so forces us to confront some of the biggest mysteries in science.
It's kind of amazing to think that for all we do know, there are still so many things we don't, even about the smallest parts of the
It
universe.
really is. And who knows, maybe one of our listeners will be the one to finally figure it out, discover some whole new way of thinking about computation.
Yeah, that would be something. Well, on that note, until next time, keep those brain cells buzzing and never stop exploring. Ever catch yourself, like, I don't know, staring at a video game and thinking, man, what if they could just make this real? Like, simulate the whole universe down to the last atom.
Yeah.
Well, you might be onto something because that's exactly what legendary physicist Richard Feynman was thinking about back in 1982. We've got excerpts from his paper, Simulating Physics with Computers, and let me tell you, it's a wild ride.
What's really interesting about Feynman's approach, though, is that he wasn't interested in just creating, like, a blurry approximation of reality. He wanted to know if a computer could perfectly mirror the universe,
Right.
replicating every single interaction. Absolute precision.
So not just like building a better version of The Sims, but actually recreating the fabric of existence itself. That's ambitious.
It certainly is, yeah. And Feynman's insights into whether this is even remotely possible have really shaped the way we think about both physics and computation ever since.
Okay, so when we talk about simulating the universe like this, where do we even begin?
Well, Feynman, he starts with a deceptively simple question. Can we simulate classical physics?
Classical physics.
Yeah, the physics of everyday objects, the stuff we learned in high school.
Planets orbiting, apples falling.
Exactly. And at first glance, it seems surprisingly doable. Classical physics has some built-in features that make it feel almost inherently computable.
Really, I gotta admit, even thinking about the trajectory of a single basketball feels pretty complicated to me.
Well, think about it this way. In classical physics, things only interact with their immediate surroundings. A basketball in flight doesn't care what a raindrop on the other side of the world is doing.
Okay.
This is a concept called locality.
Okay, that makes sense. Everything has its own little bubble of influence.
Precisely. Then there's causality, the idea that the past determines the future in a neat and orderly way, cause and effect, just like dominoes falling.
So no chance of suddenly rewinding time in a classical simulation.
Not unless we program it that way. Classical physics is also reversible, meaning that if you could reverse the direction of time, the laws of motion would still hold true.
So theoretically, we could hit rewind on the entire universe and everything would just retrace its steps.
Yeah.
That's kind of mind-blowing.
It is a pretty wild thought experiment, isn't it?
Mm-hmm.
However, there's a catch.
Uh-oh, there's always a catch. What's the snag this time?
Well, classical physics, it relies on this assumption that space, time, and all physical quantities are continuous, meaning they can take on any value within a given range. Think of a smooth, unbroken line.
Okay, yeah, I'm picturing it.
Computers, on the other hand, they're digital. They deal with discrete values represented as ones and zeros. It's like trying to recreate that perfectly smooth line using only Lego blocks.
Uh-huh.
You can get close, but you'll always have those little gaps, those jagged edges.
So to simulate even something like classical physics, we have to chop up reality into these tiny digital chunks.
Exactly. That process is called discretization.
Okay.
And while it's a necessary compromise, it introduces a fundamental limitation. No matter how small we make those chunks, we're still left with an approximation of reality, not a perfect replica.
And that approximation, those tiny gaps between the Lego blocks, could lead to big differences between our simulation and the real deal, right?
You're catching on quickly. So
Yeah.
even simulating something as seemingly straightforward as classical physics poses some pretty significant challenges. But that's just the tip of the iceberg.
Oh, no.
Remember those dominoes we talked about? Those
Right.
neat chains of cause and effect?
Yeah.
Well, get ready to enter a world where those dominoes sometimes vanish and reappear at random. Because next up, we're diving headfirst into the quantum realm.
Oh, boy. This is where I grab my helmet. Listeners, buckle up because it's about to get seriously strange. All right, quantum realm it is. But how do you even begin to simulate a universe where, as I understand it, things aren't about definite cause and effect, but rather a cosmic game of chance?
That's the million-dollar question, isn't it?
Right.
It's one thing to simulate a deterministic universe where you can, in theory, predict the exact trajectory of every particle.
Right, like our Lego block universe, even with its limitations.
Precisely. But quantum mechanics throws a wrench in the works. Instead of certainty, we have probabilities. A particle doesn't have a single definite path, but rather a cloud of possibilities, each with its own likelihood.
So instead of simulating a single predictable outcome, our computer now has to juggle an astronomical number of potential outcomes, each with its own probability. My head already hurts just thinking about it.
Yeah, you're not wrong to feel that way. It gets even more complex when you realize that the number of possible arrangements of particles, even in a tiny region of space, is, well, it's mind-bogglingly large.
Okay, let's say we somehow manage to store all that information. We build a computer the size of a planet or a galaxy just to hold all those probabilities. Can we even compute with all that data?
That's the real kicker, yeah. Even if storage weren't an issue, the computational power required to process all those possibilities would be astronomical. It's like trying to predict the exact arrangement of every grain of sand on every beach on Earth after a tsunami.
Okay, so simulating quantum mechanics by brute force is out. Is there another way to approach this? Did Feynman have any other tricks up his sleeve?
He did. Feynman, being the visionary that he was, proposed a radical idea. What if, instead of trying to force our classical computers to deal with the weirdness of quantum probabilities, we built computers that were themselves inherently probabilistic?
Whoa, hold on. Probabilistic computers? You mean like a computer that plays dice with the universe?
In a way, yes.
Yeah.
Instead of spitting out a definitive answer based on deterministic calculations, a probabilistic computer would embrace randomness as a core part of its operation. Imagine a computer that, instead of saying the answer is 32, says there's a 60% chance the answer is 42, a 20% chance it's 41, and so on.
Okay, yeah, I'm starting to see how that might be a better fit for the quantum world. Instead of trying to precisely map out all the possible quantum states, we build a computer that itself explores those possibilities, probabilistically, just like the universe it's trying to simulate.
Exactly. It's a brilliant idea, and it seems incredibly elegant. We wouldn't need to store all those astronomical probabilities, just the rules governing how those probabilities change over time.
So where's the catch this time? There's
Oh,
always a catch,
as
right?
you're learning. And yes, there's a big one. It turns out there's a fundamental incompatibility between classical computers, even probabilistic ones, and the deepest laws of quantum mechanics. A deal breaker, you might say.
Oh no, you're killing me. Don't leave me hanging. What's the deal breaker?
It all boils down to a rather peculiar concept: negative probability.
Wait, negative probabilities. How can something be less likely than impossible? That doesn't even make sense.
It's not that things actually happen with a negative probability in the real world. Instead, think of it as a mathematical quirk, a tool that physicists sometimes use in their calculations to make sense of quantum phenomena.
Okay, so it's weird, but it works on paper. But how does that break our probabilistic computer? I thought we were on a roll there.
Here's the thing. Classical computers, at their most fundamental level, deal with positive values. They can simulate randomness, sure, but that randomness is always based on positive probabilities that add up to 100%. Quantum mechanics, with its occasional need for negative probabilities, throws that whole system out the window.
Because you can't exactly have negative apples in a basket, right? It just doesn't compute.
Exactly. It's like trying to force a square peg into a round hole. Classical computers, even our imaginary probabilistic ones, just aren't equipped to deal with the full strangeness of quantum mechanics.
So we hit another wall. Is it game over for our dreams of simulating the universe?
Feynman wouldn't give up so easily, and neither should we. To really drive home just how deep this problem goes, he points to a classic experiment in quantum mechanics, one that perfectly illustrates why our classical intuition fails when we try to make sense of the quantum world.
Ooh, I love a good experiment. Lay it on me.
Picture this. An atom emits two photons, tiny particles of light traveling in opposite directions. We'll call them photon A and photon B. And we place a special crystal, called a calcite crystal, in the path of each photon.
Okay, I'm visualizing two photons, A and B, each heading towards a calcite crystal. What's so special about these crystals?
Calcite crystals have this amazing ability to split light into two separate beams, based on something called polarization. Imagine each photon as a tiny arrow pointing in a specific direction, and the calcite crystal acts like a filter, forcing the photon to go one way or the other, depending on which way its arrow is pointing.
So it's like a coin flip for photons, but instead of heads or tails, it's different polarizations.
You got it. Now here's where things get really wild. No matter how we orient those calcite crystals, if we measure photon A's polarization, we can instantly know the polarization of photon B, even though they're miles apart and haven't interacted in any way.
Hold on. Even though the photons are like shooting off in opposite directions, it's like they're instantaneously communicating with each other. How do they know what's happening on the other side of the experiment?
That's the million-dollar question, and exactly what makes quantum entanglement so mind-boggling.
Yeah.
Yeah. It seems to defy our classical intuition about, how information can travel, how cause and effect should work. Einstein famously called it spooky action at a distance, and even he struggled to wrap his head around it.
Okay, spooky is a good word for it. But how does this photon experiment tie back to our attempts to simulate the universe, on a computer? I'm starting to see a connection here, but
Right.
need help connecting the dots.
Remember those negative probabilities we talked about?
Yeah.
Well, if we try to simulate this experiment on a classical computer,
Mm.
even a probabilistic one, we hit a wall. To replicate the results, we need our computer to crunch those negative probabilities, which just isn't something a classical system can handle.
So it's like those negative probabilities are a kind of tell, a sign that we're bumping up against the fundamental limits of classical computation when it comes to the quantum world.
Precisely. It suggests that maybe, just maybe, the universe isn't bound by the same computational rules that we've imposed on our machines.
So where does that leave us? Do we need to just give up on our dreams of simulating the universe? It's starting to feel like we've hit a brick wall here.
Not necessarily, no. I think Feynman would say this is where things get really interesting. He saw this apparent incompatibility, not as a dead end, but as a challenge. Maybe, instead of trying to force-fit the universe into our existing computational models, we need to revolutionize our understanding of computation itself.
So instead of asking, can we simulate the universe, we should be asking, what is computation really, if the universe seems to be doing something beyond what our computers can achieve?
Now you're getting it. What if the universe itself is a kind of grand computation, operating on principles we're only just beginning to glimpse? What if unlocking the secrets of quantum mechanics isn't about building a better computer, but about fundamentally reimagining what computation even is?
That's a mind-blowing thought. So while we haven't definitively answered whether we can simulate the universe, we've stumbled upon an even deeper question, one that could reshape our understanding of both physics and computation.
And that's the beauty of Feynman's work, really.
Yeah.
He had this knack for asking the kinds of questions that open up entirely new avenues of exploration.
It seems like this quest to simulate the universe isn't just about, understanding the physical world around us, but about pushing the very limits of human ingenuity, human imagination.
Indeed, yeah. And who knows what incredible discoveries await us as we venture further into these mysteries of the quantum realm, guided by the insights of brilliant minds like Richard Feynman.
Ever hit play on a video game and think, what if this were the universe itself?
Well, you're channeling your inner Richard Feynman with that one.
Haha, being so.
His 1981 lecture, Simulating Physics with Computers, is our source material for this deep dive. And let me tell you, he grapples with that exact question.
We're diving into whether we could simulate the entire universe.
Not just any simulation. He was looking at if a computer could perfectly replicate the universe.
Okay, not just some approximation, but like down to the smallest detail, the quantum level.
Precisely. It's not just about the computer. It's about if we truly understand the laws of physics enough to pull it off.
So where do we even start? With our best theories, I'd imagine.
Exactly. And the first stop, surprisingly, is classical physics.
The stuff we learned in high school seems like a weird place to start for a universal simulation.
It's deceptive because on the surface, classical physics seems pretty computer-friendly.
Right. Like gravity, electricity, it's predictable, right?
Exactly. Deterministic is the technical term.
Meaning, if you know the initial conditions, you hit run, and boom, simulated universe.
Plus, it's local.
Yeah.
Things interact directly with each other at specific points in space.
Not through some weird distant connection.
And it's reversible.
Like rewinding a video.
You got it. So, at first glance, seems like a good fit for a computer program, right?
So, where's the catch?
Well, there's this pesky little thing called continuity.
Continuity.
Classical physics treats space and time as smooth, unbroken.
Okay, I think I'm following.
But computers, they chop everything up into little bits, discrete units of information.
Ah, so like trying to draw a perfect circle on a computer, zoom in close enough, and it's all blocky pixels.
A perfect analogy. And that's the problem. To simulate a continuous universe with a computer, you have to chop it up, discretize it.
And Feynman thought that could actually have measurable effects.
He did. Like maybe the speed of light, instead of being constant, might actually vary ever so slightly depending on the direction you measure it.
Whoa, so our simulation could actually be testably wrong.
Exactly. We haven't observed that kind of variation yet, but it's a theoretical possibility Feynman put forward.
Okay, so even simulating the supposedly orderly world of classical physics has hidden challenges.
And hold on to your hats because it gets way weirder when we move on to the quantum realm.
Quantum mechanics, where things go from weird to what is even happening.
Exactly. We're not dealing with certainty anymore, but probabilities.
Particles acting like waves, entanglement, all that jazz.
How do you even begin to program that into a computer?
Yeah, it's not like plugging in a formula anymore.
It's like we've gone from rendering that perfect circle to simulating the unpredictable dance of 1,000 fireflies.
Did Feynman even have a clue where to begin?
Well, he realized a regular computer, even with like unimaginable power, would struggle.
Too much to compute even for a futuristic supercomputer.
Way too much. Calculating the probabilities for every single particle in a complex system. Just impossible.
So simulating the quantum world was a dead end.
Not for Feynman. He was never one to back down from a challenge.
So what did he propose?
Get this. A probabilistic computer.
A computer that plays dice.
Essentially, instead of trying to calculate every possibility with perfect precision.
Which is impossible, as we just established.
He thought, why not build a computer that embraces randomness?
So it wouldn't give you the same answer every time.
But the key is, over many, many runs, the results would follow the same statistical spread of possibilities we see in quantum mechanics.
That's incredibly clever. If you can't beat them, join them.
Exactly. But even with this probabilistic approach, Feynman stumbled onto something truly bizarre.
And that's where these negative probabilities I've heard about come in.
You're catching on quickly.
Well, my brain is about to melt, so lay it on me.
So Feynman, he was really close to figuring out how to simulate quantum mechanics using just a regular computer.
And by regular, you mean not one of those probabilistic ones he came up with.
Right, just a classical computer. But he discovered these, well, they acted like probabilities, mathematically speaking.
But there's always a but, isn't there?
But sometimes they could be negative, and that's where things get strange.
Negative probabilities. I think I need to brush up on my quantum physics, because that just sounds wrong.
It kind of is, right? Like, in our everyday world, something can't have less than a 0 chance of happening.
Exactly. It either happens or it doesn't, right? So where do these negative probabilities fit in?
Well, Feynman, he found that to make sense of how quantum mechanics works, those negative probabilities kind of had to be there, in the math at least.
Okay, so not just a theoretical quirk, but something that was necessary to make the math work.
Exactly. And to try to explain this whole thing, he used this example with photons.
Photons, those tiny particles of light, right.
The very same. And he imagined these photons passing through a special kind of crystal called calcite.
Okay, what's so special about calcite? Does it make the photons act even weirder?
In a way, it acts like a filter. When a photon goes through calcite, it splits into 2 beams of light.
Okay, I'm picturing a prism splitting light into a rainbow.
Kind of like that. But instead of different colors, the 2 beams have different polarizations.
Polarization meaning?
It's like, imagine a wave on a string. It can go up and down or side to side, right?
Right, different ways the wave can wiggle.
Exactly. And polarization is like that, but for light waves.
So calcite sorts the photons based on their wiggle.
You got it. Now imagine you've got 2 of these calcite crystals, one after another.
Okay, I'm with you so far.
We send a single photon through the first crystal, then take one of the beams, just one polarization, and send it through the second crystal, which is turned at an angle.
Okay, so even though we already know how the photons are polarized from the first crystal, the second one can still measure them as having a different polarization depending on how it's turned.
You're getting it. Now, instead of just one photon, imagine we use 2, but these photons are entangled.
Entanglement, that spooky action at a distance stuff.
The one and only. And experiments show it's a real thing no matter how weird it seems.
Okay, 2 entangled photons, each going through a calcite crystal, and this is where those negative probabilities come into play.
Exactly. Feynman, he figured out that if we tried to simulate this whole experiment on a regular computer, assuming there were some hidden variables determining which way the photons would go.
Hidden variables, meaning something we haven't figured out yet that's controlling things behind the scenes.
Right. But if we assume that, our measurements of the 2 entangled photons, they would only agree at most 2/3 of the time.
2/3. So our simulation is wrong a third of the time. That's not a very good simulation.
And here's the thing. Quantum mechanics, it predicts, and actual experiments confirm that the probability of the measurements agreeing can be even higher, like 75%.
So our classical computer simulation just can't keep up with the quantum reality.
It struggles with that extra 9% agreement.
Which doesn't sound like much, but...
But it's a huge deal. It means to get those probabilities up to what quantum mechanics predicts, you have to allow for those negative probabilities, even though they make no sense in the classical world.
So we need a new kind of math to even describe what's going on.
That's what Feynman seemed to be suggesting.
And that's where the idea of a probabilistic computer comes back in.
That was one of his ideas. Maybe by building a computer that embraces randomness, we could bridge this gap.
So it's not just about the computer, it's about our fundamental understanding of probability itself.
That's the real mind blower here. Feynman, he wasn't just trying to simulate the universe. He was questioning the very tools we use to describe it.
So where does this all leave us? Can we simulate the universe on a computer? I feel like Feynman was asking a question he wasn't even sure he wanted the answer to.
Well, that was Feynman. Always pushing the boundaries, even if it meant challenging what we thought we knew.
We started with simulating the universe, and now we're questioning the nature of reality itself. Did Feynman ever, have any answers?
Feynman was less about the answers and more about asking the really, really good questions. Remember his idea for a quantum computer?
Right. Building a computer out of quantum stuff to simulate quantum mechanics, like fighting fire with fire.
Exactly. He believed that might be the key to unlocking this whole simulation problem.
But could a quantum computer, even a super powerful one, actually simulate the entire universe?
It's a question that's still up for debate, even today.
It's incredible that he was already thinking about this stuff back in the 80s.
Feynman was way ahead of his time, and he even admitted that it wouldn't be easy. He famously said, "Nature isn't classical, damn it."
Haha, classic Feynman.
And if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy.
He makes it sound almost like a challenge, a dare to all the physicists who came after him.
He had a way of inspiring people like that. Even without all the answers, he left us with some amazing, thought-provoking questions.
So what would Feynman say to the researchers today who are still wrestling with these mind-bending ideas?
I think he'd encourage them to embrace the mystery, keep pushing those boundaries, and never stop questioning. Who knows what incredible discoveries are still out there, just waiting to be uncovered.
It's like by trying to simulate the universe, to build these complex models, we might stumble upon an even deeper truth about how it all works.
Exactly. It's about the journey as much as the destination, right?
Absolutely. This deep dive has taken us from simulating classical physics to grappling with the weirdness of quantum mechanics and those baffling negative probabilities.
And it all goes back to the brilliance of Richard Feynman, a true visionary who challenged us to see the universe in a whole new light.
He wasn't just a brilliant physicist, he was an incredible teacher who reminded us to always stay curious, to question our assumptions, and to never lose that sense of wonder about the universe and our place in it. So until next time, keep exploring, keep those questions coming, and we'll catch you on the next deep dive.
Ever wish you had a quantum physicist on speed dial to, break down the really mind-blowing stuff?
Well, today's your lucky day because we're tapping into the mind of Richard Feynman.
We're diving deep into his 1981 lecture, Simulating Physics with Computers.
It's a wild ride.
Big question. Can we build a computer so powerful it could simulate the entire universe?
Feynman starts with this deceptively simple question. Can a computer even theoretically perfectly simulate physics? But he sets these ground rules, and those are crucial.
Yeah, it's like he's laying down a challenge, right?
Absolutely. The simulation has to be exact. No shortcuts, no rounding errors. And the computer's size has to directly correspond to the system being simulated. You can't build a computer bigger than the universe to understand the universe.
That defeats the purpose.
It's like, what are the fundamental limits of both computing and the universe itself? And when you start thinking about it that way, even simulating something like classical physics gets tricky. Like, how do you even simulate time itself on a computer? It's something we take for granted.
Right, I ask.
And then there's anisotropy.
Anisotropy.
The idea that physics might work differently depending on direction. Like, imagine gravity pulls you down faster than it pulls you to the side.
Oh, okay, I get it. Like, the rules rules change depending on which way you're facing.
Exactly. And that's just classical physics. We haven't even touched quantum mechanics.
And that's where things go from complicated to, like, whoa.
Because now we're not just talking about a giant clockwork universe, we're talking about a universe that plays dice with reality.
And how do you even begin to program that?
You hit the nail on the head. The problem is, to simulate quantum mechanics, you'd need to store the probability distribution for a massive system, essentially every possible outcome. And that's impossible. Even with a crazy powerful computer, there's just too much information.
So are we stuck? Are our universe simulating dreams doomed?
Well, Feynman had a trick up his sleeve. He proposed probabilistic computers.
Probabilistic computers sounds intriguing.
Instead of calculating and storing all those probabilities, what if we could build a computer that embodies probability, just like the quantum world does?
So instead of crunching numbers to figure out the odds, it becomes the odds.
Exactly. And that's where the idea of quantum computers comes in. And believe it or not, we get some hints about this from something called solid-state physics.
Okay, now we're really going down the rabbit hole. How does studying solids relate to building a quantum computer?
It's all about the electrons. The way they behave within the structure of a solid material can actually, mathematically, mimic the behavior of particles in quantum field theories.
So it's like those patterns you find in nature that repeat on different scales, like the spiral of a seashell and the spiral of a galaxy.
That's a great way to put it. And this led Feynman to ask this groundbreaking question: could a system of simple two-state quantum elements, think of those electrons, simulate any quantum system, maybe even the universe itself?
So hold on, you said earlier that classical computers couldn't simulate quantum mechanics. Now are we saying they can?
It's not a contradiction, but it is about to get even more mind-bending. Feynman comes back to that question: can a classical computer, the kind we use every day, simulate quantum mechanics? And the answer initially seems like a hard no.
But there's always a but with Feynman.
There is. And to understand it, we need to take a trip to the world of density matrices and the Wigner function. These are mathematical tools that help us represent those tricky quantum states.
I'm guessing these aren't concepts you just throw around at parties. Can we get a visual here?
Think of the Wigner function like a quantum weather map. Instead of just showing temperature, it shows the probability of different weather conditions happening at a single point. So you might see a 70% chance of sunshine, 20% chance of clouds, and even a small chance of like a sudden hailstorm, all in the same spot.
Okay, so it's like a weather forecast on a quantum scale. All those possibilities layered on top of each other. I kind of get it, but what's the but?
The but is the Wigner function looks like a regular probability distribution until it doesn't. Sometimes it can have negative values, and that throws a major wrench in our classical simulations.
Negative probabilities. What does that even mean?
That, my friend, is the heart of the mystery. And to really understand it, we need to look at one of Feynman's most elegant thought experiments. This one dealing with the polarization of photons. All right, so picture this. We've got a source that's shooting out pairs of photons, and these photons, they're entangled.
Okay, so they're linked in that spooky action at a distance kind of way.
And let's say you're observing one of these photons, and I'm observing its entangled buddy.
Gotcha. We each have our own photon. What do we do with them?
Well, we each have a calcite crystal.
Oh, like those things that split a beam of light.
Exactly. They split light based on its polarization.
Right. I remember that from physics class. You shine a light through, and it comes out as two beams bent at different angles.
And we can adjust the angle of these crystals to measure different polarization states of the photons. And here's where things get really wild. Quantum mechanics, it makes very specific predictions about the correlations we should see between our measurements. Let's say you measure your photon and find that it's vertically polarized.
Then you know instantly that mine will also be vertically polarized.
Yeah.
Even though they're miles apart.
Exactly. It's like they're communicating faster than light, which, spoiler alert, they're not. But it's a real head scratcher. Anyway, the point is, you can't reproduce these exact correlations on a classical computer. Unless.
There's always an unless.
Unless you introduce negative probabilities into your model.
Wait, negative probabilities? Like less than 0% chance of something happening? How does that even make sense?
That's the million-dollar question. And it gets to the heart of why simulating quantum mechanics on a classical computer is so tricky. See, to simulate this experiment on a classical computer, we'd have to, in a sense, pre-program each photon with hidden information, like a secret code.
So it knows whether to go straight or bend at a certain angle when it hits the crystal.
Exactly. But because these photons are entangled, those secret codes, they'd have to be correlated in this way that just doesn't jive with regular probabilities. The math just doesn't work out.
So we're talking about a different kind of probability here.
Completely different. It's like we're trying to describe a round peg with a square hole. To make the classical model match the experimental results, we'd need probabilities that go negative.
It's like saying there's a negative chance of rain. It just doesn't compute, literally.
Exactly. It highlights this fundamental clash between how we understand the world classically and what's actually happening at the quantum level. Our classical intuition just breaks down.
So are we stuck? If we can't simulate these quantum quirks without resorting to impossible negative probabilities, does that mean our dreams of a universe simulating computer are doomed?
Not necessarily. Remember those quantum computers we talked about earlier? This is where they come back into play.
Because they play by a different set of rules.
Exactly. If we could build a computer that operates using the principles of quantum mechanics superposition entanglement, then we might have a shot at creating a machine that truly speaks the language of the universe.
It's like we need a whole new operating system, not just a software update.
Precisely. And the implications are huge. Think about it. Medicine, material science, artificial intelligence, all these fields could be revolutionized by quantum computing.
So we started with this seemingly simple question, can we simulate the universe? And it's led us down this rabbit hole of quantum mechanics, negative probabilities, and questioning the very nature of reality itself. It's mind-blowing.
And it gets even deeper. Feynman, at the end of his lecture, he posed these really profound questions about the nature of probability, the limits of free will, even whether our perception of randomness is just an illusion.
Okay, whoa. Let's unpack that. But first, can we just acknowledge how incredibly wild this all is? So much to think about. But I keep coming back to this idea that randomness, like that fundamental unpredictability in quantum mechanics, it might be an illusion? Is that really what Feynman was getting at?
Yeah, it's a tricky concept, but that's Feynman for now. Always pushing the boundaries. He was suggesting that because we're stuck in this universe, we're only seeing a tiny slice of the bigger picture. What if, and this is a big what if, there's some being outside of time able to see the entire evolution of the universe all at once?
Like a cosmic time traveler with the ultimate God's eye view. So what would they see?
Well, to them, what we perceive as random, it might look like a perfectly determined sequence of events. They see all the cause and effect, the interconnectedness across all of time. It's not random to them, just to us, because we're stuck in the middle of it.
It's like, have you ever watched a movie for the first time and there's a big twist and you're like, whoa, where did that come from? But then you watch it again and you start to notice all those little hints they dropped along the way, the foreshadowing. It wasn't random, you just didn't have the full picture yet.
Exactly. It makes you wonder, what don't we know? How much of what we perceive as reality is just a product of our limited perspective?
Like, whoa, dude, am I even real?
Okay, maybe not that extreme.
But seriously, it makes you question everything.
Oh.
But that was Feynman's gift, right? He wasn't afraid to ask those big, weird, uncomfortable questions, the ones that don't have easy answers.
And in doing so, he opened up these new paths, not just in physics, but in how we think about computing, about consciousness, about the very nature of reality. He made us realize there's so much more out there than we can even imagine.
It's mind-blowing. So where do we go from here? What's next in this quest to maybe one day simulate the universe? Or at least get a little closer to understanding it?
Well, we're just getting started. Quantum computers are still in their infancy, but they have the potential to completely change how we approach complex problems. And as we delve deeper into quantum mechanics, who knows what we'll find?
I feel like we're constantly on the verge of some major breakthrough. It's a really exciting time for science.
Definitely.
Well, I think that about wraps it up for this deep dive. We've gone from simulating physics to exploring the weirdness of quantum mechanics to questioning the very fabric of reality. And you know what? I wouldn't have it any other way. So to everyone listening, keep asking those big questions, keep exploring, and keep your minds open to the wonders of the universe, both real and simulated.
Okay, so get ready because we are diving into something huge today.
Yeah.
Something that makes, like, is there life out there? Seem almost like a small question. We're tackling whether we can simulate the entire universe, the whole shebang, on a computer.
It's a big one.
It really is. And to guide us through this, we have Richard Feynman.
The man, the myth, the legend.
Right? I was going through this lecture that you sent over, and I was just thinking, this guy was wrestling with some serious, serious concepts.
Well, and you know what I find so fascinating about Feynman? He doesn't just jump into the technical stuff. He starts by reframing the question entirely. So instead of, can we do this, it becomes, what would it even take to get us there?
Oh, that's good. Yeah.
It's like he's laying the groundwork for, I don't know, almost like a new philosophy of reality, not just a science project.
Yeah, he really is. It's like he's questioning the tools and the rule book all at once.
Absolutely. And that leads him to these really fundamental questions like, what even is a computer,
Yeah.
at its core? And can physics, as we understand it now, even handle something as complex as simulating the entire universe?
Yeah.
So he comes up with this thought experiment. He imagines this ideal computer, but not the kind we're used to with circuits and processors and whatnot. He's talking locally interconnected elements.
Okay, I remember that phrase jumping out at me. Why locally interconnected elements? It seems kind of, I don't know, limited maybe.
It all goes back to mirroring nature. See, in physics, at least the classical kind, everything's local. Gravity, for example. Earth doesn't instantly feel a star millions of light years away, right? It's all about the sun, our close neighbor.
So it's like he's saying, to build this universe simulator, the computer itself has to be structured like the universe.
Exactly. Information traveling locally, interactions happening on that level, just like reality. It's not about brute force, just bigger, faster computers. It's got to be designed with the universe's structure in mind.
Okay, that's wild. But this is where I assume things get even more complicated, because now we have to throw quantum mechanics into the mix. And everyone knows quantum mechanics, that's where things get really weird.
Oh, absolutely. Simulating classical physics is one thing. Crazy complex, don't get me wrong.
Yeah.
But possible, right? Lots of equations, tons of processing power, but doable in theory.
Yeah, like if you were building a super detailed model of like our solar system or something, right? Difficult, but not impossible.
Exactly. But quantum mechanics, that throws a wrench in the whole thing.
Yeah.
Because now you've got inherent randomness, fundamental uncertainty in how things work. It's not about predicting exact outcomes anymore. It's about probabilities.
Right, like the difference between calculating where a ball will land versus programming a computer to perfectly flip a coin.
Perfect analogy. Because with the coin flip, you've got that randomness. You can't pin it down. Classical physics, you know the starting point. You could predict everything perfectly. In theory, quantum world, forget it. You're dealing with chance, with uncertainty baked into reality itself. And that, as you can imagine, has huge implications for simulating the universe.
Okay, so quantum mechanics, randomness. How do you even start simulating something like that? Did Feynman just throw in the towel?
Oh, no, not Feynman. He loved the challenge. He actually starts by looking at like the actual computer power you'd need. Imagine trying to simulate not where a particle is, but all the places it could be and the probabilities for each one. That alone is tough.
Yeah, I'm picturing like one particle, a cloud of maybes. Okay, I can kind of see it.
Now add another particle. The possibilities don't just double, they explode.
Yeah.
Because you've got particle A's maybes interacting with B's maybes. And each time you add another particle.
It's like exponential growth, right? Out of control.
Exactly. Even with insane computers just representing all that, let alone simulating how it changes over time. Impossible.
And we're still talking, what, a handful of particles? Not the entire, like, universe worth.
Precisely. So simulating it head on, not going to happen. So Feynman thinks, what if, instead of fighting this randomness, what if the computer was built on it? A probabilistic computer.
Whoa, a computer that plays dice with the universe. That's wild.
Right. And to wrap his head around this, he uses this thing called the density matrix.
Catchy. Density matrix. Not exactly something you work into casual conversation.
Right. But bear with me, it's cool, I promise. Imagine predicting the weather. You don't just say rain or shine, right?
Right. You've got percentages, chances.
Exactly, like 70% chance of showers. Density matrix is kind of like that, but for quantum stuff. Keeps track of all the states a particle could be in and how likely each one is.
So instead of it is here, it might be here, it might be there, all those maybes.
Exactly. Like instead of one path, you're tracking every path it could take all at once.
Ugh.
And Feynman's thinking, maybe with a computer handling that, we can crack quantum mechanics.
Okay, bold plan. But could he even build a probability-powered computer?
Well, here's where things get really trippy. Turns out, the math for this quantum probability stuff, it's almost identical to the regular kind, except for one tiny, but huge detail.
Okay, I'm getting a but feeling here.
But sometimes you get negative probabilities.
I'm again.
Yeah, it's like saying there's a negative chance of finding the particle somewhere.
But that's like, how can something be less likely than impossible? That doesn't even...
Exactly. Makes zero sense in our normal world. And that's the point. It breaks our logic. This negative probability thing, that's the wrench in the whole plan. Simulating that on a normal computer. No way.
So, negative probabilities. Sounds made up. But you're saying there are experiments that show this, like proof that our regular logic just crashes when it comes to this quantum stuff.
We're telling me, and Feynman uses this really cool experiment with, get this, entangled photons.
Okay, already sounds complicated. Hit me. Entangled photons, what even?
So picture this. Two photons born together, they get shot off in opposite directions, like beams of light, each with one photon inside zooming across the universe. One's coming towards you, one's coming towards me, and we're like light years apart.
Okay, lots of space. Got it.
We've each got this thing called a photon detector, right? It can measure this thing, this property the photon has, called polarization.
Okay, so two photons, two faraway people, two detectors. What's this polarization thing do?
Think of a photon like a tiny little arrow flying through space. Polarization is which way the arrow points.
Yeah.
Up, down, sideways, somewhere in between.
Okay, makes sense.
But here's the wild part, right? Entangled photons, they're linked up, deeply linked. Doesn't matter how far apart they are, if you measure one's polarization, you instantly know what the other one must be.
Instantly, like faster than light, instant.
You got it. Spooky action at a distance, Einstein called it. And here's where our brains break, okay? Because this messes with everything we thought we knew.
All right, yeah, I'm seeing where this is going.
So we've got these entangled guys, our detectors. You measure yours, and it's, say, vertical. Because they're entangled, mine, without even looking, has to be horizontal. Always opposite.
Right, because they're linked up, the entanglement thing. But I thought we were talking negative probabilities. Where's that come in?
This is where it gets trippy, okay?
Yeah.
Feynman showed that if you try to explain this experiment, but using classical physics, right, to like each photon's got secret instructions or something.
If he does that, I do this, that kind of thing, like a pre-planned code.
Exactly. Even with that, with those hidden instructions, the math doesn't work out. Classical physics says the most you can match polarizations, using vertical, me horizontal, is 20/3 of the time.
Okay.
But in reality, in these experiments, it's 30/4.
So that tiny difference, that's what tells us something's up.
Exactly. It's like the universe goes, nope, wrong rule book, buddy. That's a sign. Classical thinking. Can't handle this quantum world.
So what's the answer then? Could Feynman simulate the universe, or was this game over?
Well, he didn't exactly solve it, but he did something better. He challenged everyone to think differently. Maybe it's not about bigger, faster computers, but a whole new kind of computer, one that uses probability, entanglement as features, not bugs.
So instead of forcing the universe to fit our computers...
We build computers that fit it. Quantum computers, they use that weirdness, that superposition. That's maybe the key.
It's like we're trying to understand a language no one's ever spoken before.
That's a great way to put it. And who knows, maybe chasing the simulation dream, asking these crazy questions, that's how we'll figure out not just new tech, but what reality is.
And on that note, we'll leave you with this. If we could simulate the universe, would we even recognize it? Would the beings inside, would they know? Something to think about. Until next time, keep asking the big questions.